All right, so chapter 4 is all about variability in statistics. And when we think about variability, we can describe it in a number of different ways. It can be described as a quantitative distance measure based on the differences between scores, and it can also describe the distance of the spread of scores or distance of a score from the mean. The whole purpose of these measures of variability are to describe the distribution, whether it's clustered or spread out, and to also help measure how well an individual score is representative of the distribution of scores. If we take a look at figure 4.2, we can see a population distribution that describes adult heights and adult weights. You can see that both of those follow a bell curve, but the ranges of scores are quite different. There are 4 ways that we can measure how scores vary. We can look at range, interquartile range, variance, and standard deviation. The range is going to be the distance covered by the scores in a distribution, from the smallest score to the largest score. For continuous variables, real limits are used. And for that, the formula will be range equals upper real limits, or URL, for X max minus the LRL, which are the lower real limits, for X minus or X minimus. So when we have discrete variables, the range is going to be described basically as the maximum score in the distribution minus the minimum score in the distribution. So it's always going to be based on 2 scores, not every score in the distribution. And because of that, it can be imprecise, it can be an unreliable measure of variability. Interquartile range is based on quartile scores, and they are the scores that have percentile ranks, such as 25%, 50%, 75%, and 100%. These are usually called the first, second, third, and fourth quartiles, respectively. So 25% would be the first quartile, 50% would be the second quartile, 75% would be the third quartile, and 100% would be the fourth quartile. These also help us divide the distribution into 4 equal parts that correspond to 25%. When we have interquartile ranges, we're going to look at that as IQR, and it's the distance between the X values that correspond to the first quartile and the third quartile. Scores should fall in the middle 50% of the distribution. If we look at figure 4.3, we can see those interquartile ranges, and we can see how they're indicated for a distribution of scores. We can see that the middle 50% of the distribution consists of those scores between the first and third quartile, as indicated on the chart. When we want to define variance and standard deviation, we can look at these 2 concepts as the most common and most important measures of variability and standard deviation. This is what you would primarily use whenever you're conducting experimental research. It's a measure of the standard or average distance from the mean, and it also can help us describe whether the scores are clustered closely around the mean or widely scattered. Our calculation often differs from population and samples when it comes to variance and standard deviation, and variance is going to be a necessary companion concept to standard deviation, but they are not necessarily the same concept. These 2 concepts can also be the hardest for students to understand, so I really want you to make sure that you pay attention so that you'll understand how variance and standard deviation differ. So if we want to look at standard deviation, the first thing we're going to do is determine the amount of deviation. And we're talking about how much a score deviates, or the distance between a score and whatever is the mean. And you can see the formula for that. The second thing we want to do is we want to find a sum of deviations to use as a basis for finding the average deviation. There could be two problems with that. The deviations could sum to 0 because M is a balance point, or if the sum is always 0, that means that the deviation is going to also always be 0. So it's always good to have a different strategy for figuring out how much the score deviates from the mean. The third step is to remove negative deviations. So the way you can remove a negative deviation is to first square each deviation score, then sum the squared deviations, average those squared deviations, take the mean of those squared deviations, and that is what is known as the variance, and then your variability will be measured in square units. So when we think about that, our variance equals the mean of those squared deviations, which are the distance. And that average squared distance is what is happening from the mean. And then in step 4, the goal is to compute a measure of the standard average distance of the scores from the mean. Variance is going to measure the average squared distance from the mean, which is not really what we're looking for. But if we adjust by squaring each distance to find the average of the squared distances, and we take the square root of the variance, then we can get our standard deviation. And that is how we measure standard deviation, by taking the square root of the variance after it has been doubled. Figure 4.4 shows you kind of a flow chart of how we can calculate variance and standard deviation to make it work based on what I just spoke about. Figure 4.5 gives us a frequency distribution histogram for a population of 5 scores. We can see that the mean for the population is 6. The smallest distance from the mean is 1 point, and the largest distance in the distribution is 5 points, which means that our standard distance, or our standard deviation, should be somewhere between 1 and 5 points. When we get ready to measure the variance and standard deviation for a population, we can look at our variance formula as the sum of squared deviations over the total number of scores. So the sum of scores, the SS, is going to be the sum of the squared deviations of scores from the mean. Those two formulas are used for computing the sum of scores. So we've got our definitional formula and the computational formula for sum of squares. So as you're using these computational formulas in your assignments, you always have to exercise caution, because you need to remember that these 3 formulas are often mistaken, and they are not the same, and they're not going to give you the same results. Well, when we want to find a formula or a notation, we can locate a formula for population variance and population standard deviation using those formulas you see below. For notation, if we are trying to anticipate what the values are for notation, we have to look at the variance. We have to look at variance as the average of squared deviations so we can identify how the population is varying. And we do so with the lowercase Greek letter sigma squared. And then our standard deviation is the square root of the variance. So we identify that with the lowercase Greek letter sigma. So we're continuing to add more and more formulas for you to understand standard deviation. Let's go ahead and take a little bit of a learning check. Here are some true-false questions for you to answer. The first question is, the computational and definitional formulas for sum of squares sometimes give different results. And the second one, if all the scores in a data set are the same, the standard deviation is equal to 1. Give you a few moments to think about your answer choices. And both of these are actually false statements. The computational formula is just an algebraic rearrangement of the definitional formula, and the results are going to be identical. And then for the second statement, when all of the scores are the same, which means they're equal, then their deviations are going to be 0. And that's going to be their standard deviation versus 1. Here's our second learning check. It is a multiple choice question. The standard deviation measures the A, sum of squared deviation scores, B, standard distance of a score from the mean, C, the average deviation of a score from the mean, or D, the average squared distance of a score from the mean. I'm going to give you guys a few moments to think of the correct answer choice. And that standard deviation is going to help us B, measure the standard distance of a score from the mean. When we want to measure variance and standard deviation for a specific sample, which is the goal of inferential statistics, we can do that to draw conclusions about the populations and to make a basis of limited information from a sample. Samples, we know, can differ from the population. We try to make them as representative of the population as possible, but they can differ. Samples, though, have less variability within the actual sample itself. So when we compute the variance and standard deviation in the same way as we do for a population, that would give a biased estimate of what the population values actually are. If we take a look at figure 4.6, we can see the population of adult heights from a normal distribution. If you select a sample from this population, then you're going to be more likely to obtain individuals who are near average in height. As a result, the variability of the scores in the sample is going to be smaller and less spread out than the variability for the scores in the population. So we've got a few formulas that help us measure sample variance and standard deviation. So just like the sum of squares is computed, which we talked about before, the formula for variance has n minus 1 rather than big N as the denominator, and notation uses S instead of the sigma symbol. If we look at figure 4.7, we can also see a frequency distribution histogram for a sample of 8 scores. Sample variability and degrees of freedom let us know about population variance. And when we have population variance, our mean is known. Deviations are computed from a known mean. We also can have sample variance as an estimate of the population when our population mean is unknown, and we use sample means that restrict variability. When we're looking at degrees of freedom, the number of scores in the sample that are independent and are free to vary will be noted to us. Those degrees of freedom, which are DF, for a sample is usually n -1. Let's go ahead and have a second learning check. If we have a sample of 4 scores, which has a sum of square that's equal to 24, what is the variance? Is it A, 6, B, 7, C, 8, or D, 12? Let me give you guys a moment to think about what the correct answer might be. And our correct answer is actually going to be 8. Our second learning check is true-false. A sample systematically has less variability than a population. Is that true or false? And the standard deviation is the distance from the mean to the farthest point on the distribution curve. Take a few moments and think whether either of these answers are true or false. And we have one true statement and one false statement. Extreme scores do affect variability, but they're going to be less likely to be included in a sample. The second statement is false because the standard deviation is going to extend from the mean approximately halfway to the most extreme score. As we start to look at sample variance as an unbiased statistic, we need to understand that an unbiased estimate of a population parameter provides us with an average value of statistics, which equals the population parameter. The average value uses all possible samples for a particular sample size. The corrected standard deviation formula produces an unbiased estimate of the population variance. And those biased estimates of population parameters are going to systemically overestimate or underestimate the population parameters. So if we look at table 4.2, this table illustrates with a known population that both the sample mean formula and the corrected sample variance formula is going to produce unbiased estimates of their corresponding population parameters. Here's a little bit more about variance and standard deviation. Means and standard deviations are going to be particularly useful in clarifying graphs of distributions. Those means and standard deviations together can provide extremely useful descriptive statistics for characterizing distributions as well. When we present the mean and standard deviation in a frequency distribution graph for both populations and samples, it's going to be easy to represent the mean and the standard deviation. A vertical line in the center usually denotes the location of the mean, and a horizontal line to the right or left is going to denote the distance of one standard deviation. So here we can see that figure 4.9 shows the means and standard deviations in frequency distribution graphs. For graph A, we've got a population distribution with a mean of 80 and their standard deviation of 8. And in figure B, we have a sample with a mean of 16 and a standard deviation of 2. So we can see how those things could be graphed out. When we look at transformations of scales, this is how we can add a constant to each score or multiply each score by a constant. If we add a constant to each score, then that means our mean is going to change because something's going to be added. In that case, though, the standard deviation should still remain unchanged. However, if we multiply each score by a constant, the mean's going to be changed and the standard deviation is going to be changed. And the standard deviation is also going to be multiplied by the constant. When it comes to descriptive statistics, a standard deviation is going to describe scores in terms of how much they differ or what distance there is from the score to the mean. They're also going to help describe an entire distribution with just two numbers. And it'll give us a reference to both, which allows reconstruction of the measurement scale from just these two numbers. We can see that represented in figure 4.11, which is where we have a sample of 20 scores with a mean of 36 and a standard deviation of 4. When it comes to variance in inferential statistics, the goal of inferential statistics is always to detect meaningful and significant patterns in research results. That variability in data is going to influence how easy it is to see patterns. If we have high variability, it can obstruct patterns that would be visible in low variability samples. And variability is often classified as error variance in the context of inferential statistics, which tells us the sample variance represents unexplained and uncontrolled differences between those scores. So if we take a look at figure 4.12, we can see that these graphs show the results from two experiments. In experiment A, you've got the variability, which is small and easy to see that there's a 5-point mean difference between the two distances or the two treatments. And then in experiment B, the 5-point mean difference between the treatments is obscured because there's so much variability. So let's go ahead and do another learning check. A population has a mean of 6 and a standard deviation of 2. Each score is multiplied by 10. What is the shape of the resulting distribution? I'm going to give you guys a few moments to think of which answer might be correct out of A, B, C, and D. And that correct answer is indeed C. Let's have another learning check. True, false. A biased statistic has been influenced by researcher error. True or false? And on average, an unbiased sample statistic has the same value as the population parameter. Take a few moments and think about whether these statements are true or false. The first one is false because bias refers to the systemic effect of using sample data to estimate a population parameter. And for the second one, that is a true statement. Each sample's statistic differs from the population parameter, but the average of all samples will equal the parameter. And one of the last things I want to discuss is the SPSS summary table that's associated with the example in 4.6. And you guys can see that this table shows us those descriptive statistics for the sample size of 8 scores. And if you look on page 126 of the textbook, it will give you more information about this particular sample. So I hope you guys understand a little bit more about variance and how scores can deviate from the mean.